I think I've made this point already, and you should be familiar with it now. Lean mixtures are faster to ignite at high temperature and low pressure. Okay, and we're just looking here at butanol isomers. So we have sec-butanol and isobutanol. And both of these studies were performed at high temperature. So you can see we're starting here at 1250 Kelvin, going up to maybe 1700 Kelvin. And you can see lean mixtures with 12% O2 are much faster than the rich mixture here with 3% O2. Why? Because H plus O2 gives O plus OH. The rate of that is much faster in the lean case compared to the rich case because the concentration of O2 is way higher. That's it, right? And the same here for isobutanol, right? Similar result. Okay. And then here we have isopentanol at 21 bar. So rich mixtures are faster at low temperature and high pressure. Okay. So you can see here we have lean, stoichiometric, rich. But here we're at 1,000 going up to, I don't know, 1,300, 1,350 Kelvin, right? And you can see even out here, the model is predicting that rich mixtures are faster than the stoichiometric, which are faster than the lean, okay? So that's just, and just to remember that, okay? And here, and then I was trying to pick ones where you can see the turnover and the transition from low temperature to high temperature. I showed you constantly there for M-pentane, but these are data. It's hard to actually see it actually when we take the experimental data, right? Here we have data for, these are 5-component natural gas mixtures, okay? So we have methane, ethane, propane, butane, and pentane, okay? And this mixture has a much higher concentration of higher hydrocarbons. Their concentrations are twice those compared to here. So here we have 20% ethane, here we have 10% ethane, and so on. And you can see here that you can see a lot more negative temperature coefficient behavior at low temperature. But again, at low temperature, rich mixtures are faster than the stoichiometric, which are faster than the lean. But we reach a ceiling temperature here of 1,300 Kelvin, above which then you can see that the lean mixture is becoming faster than the stoichiometric, and the rich mixture is slowest. Okay, and there is some transition here, but it's not as clear cut. Okay, and again, we see it for propylbenzene at 30 atmosphere. We took these data, and you can see here that the lean are becoming fastest, the rich the slowest, and that there's some sort of a turnover here at 1250, 1300 Kelvin again. Not a sort of a turnover. There's a crossover in the chemistry. You can see that clearly. Okay, that's just accentuating it. Okay, so that's a synopsis of, we'd say, you know, you're looking at low temperature, high temperature. Where does it transition? It depends on the pressure that you're at, but typically in that 1,200, 1,300, 1,350 Kelvin range is a good rule of thumb. Right. Okay. So how do we assign rate rules for the reaction classes then for large hydrocarbon species? Okay, I've kind of been, I haven't gotten there. So we have high temperature reactions, unimolecular fuel decomposition, H atom abstraction. So where do we get the rate constants for these reactions is really the question, right? So and we're using this test molecule 2-methylheptane. So if we take this molecule, we have a methyl group at the end, so the primary hydrogen atoms. Then we have the methylene groups in the middle, so they're all secondary hydrogen atoms. Then we have a tertiary hydrogen atom here, where it's bonded to a primary and 2 secondaries. Okay, and the bond association energies typically, the primary, as I said, is 101.1 or 101.5 kilocalories per mole, secondary 98.5, and tertiary 96. Okay, so unimolecular fuel decomposition is very important in predicting ignition delay times in a shock tube, right? And typically from about 1,100 Kelvin and above, regardless of the pressure, right? So when you're 1,100, 1,200 Kelvin and above, unimolecular decomposition ignition delay times is sensitive to the rate constant that you use for this. Right? So we usually estimate the high pressure limit in the reverse exothermic direction, radical-radical recombination, which, as I said the other day, has no activation energy. And then we calculate the forward rate constant, taking the thermochemistry into account. Okay, so that way we have delta H reaction, but it's all delta H reactions, nothing else, right? So the activation energy in the reverse direction is 0, and then the forward activation energy is just delta H reaction. But we let the code do that calculation itself, right? But we usually need to account for fall off in the rate constant. I talk about that a little bit. Okay, so the high pressure limit, then we can have CH bond scission. So for instance, 4-methyl 1-heptyl radical reacting with hydrogen atom would give you 4-methyl heptane. And for any H atom reacting with any radical, any alkyl radical, we estimate a reverse rate constant of 10 to the 14 for that. Okay, and then we do some fitting to calculate rate constant as a function of pressure. Okay. For then methyl radical adding to a radical, we typically use a rate constant of 10 to the 13, right? And then for maybe ethyl, we decrease it. So here we have C1, here we have C2, then we'll have C3. If we have a larger radical adding to, well, what in this case would be a progressively smaller radical, we typically decrease the rate constant slightly, because the rate of reaction from simple collision theory depends on the square root of 8 RT over pi mu, where mu is the reduced mass. And the reduced mass of ethyl will be quite a bit bigger than the reduced mass of methyl. Okay, so we slightly decrease it. But again, I did this the other day, on Monday, and I showed you this slide where you've got the frequency for the, so if I'm estimating methyl plus methyl, right, and that's 10 to the 13, and then I have ethyl plus methyl and propyl, I'll be coming to that in a minute, okay? I'm going to have about the same rate constant. Maybe the frequency factor might be slightly different, right, every time, but no activation energy barrier, right? And then I'm estimating the rate constant in the forward direction from thermochemistry. Well, the thermochemistry is going to depend on the reverse frequency factor and on the exponent of delta S, the exponent of delta S over R. And as I said the other day, that's equal to the exponent of the group contributions to the species, the entropy change for the group values divided by R, times the symmetry number factor, which is the symmetry number of the reactant divided by the product of the symmetry numbers of the products. Okay, so if we consider something like neopentane, and I had this in the notes, but I did it quickly on the board for you the other day, we'd say neopentane gives you terbutyl plus methyl. Okay, the delta S over R the symmetry number factor is equal to 4, right? Whereas if we take N-pentane, the symmetry number factor is actually 0.5, right? So just based on symmetry number factor, right, the unimolecular decomposition in neopentane will be 8 times faster than that of N-pentane, right? Just based on that. But it's not just based on that, okay? We also have the group value factor. And the group value factor will compensate somewhat for that factor of 8. So neopentane unimolecular decomposition is not 8 times faster than N-pentane, but it will be faster because of that symmetry number factor, okay? And we do see it, that neopentane, unimolecular decomposition in neopentane is more important than it is for N-pentane and isopentane, right? So that does come out, okay? And this, okay, so this is true, okay? So unimolecular fuel decomposition, there was a nice paper published by Stephen Klippenstein co-workers in PCCP in 2006, where he looked at the rate constants the rate constants for recombination of methyl plus ethyl, methyl plus isopropyl, methyl plus terbutyl, ethyl plus isopropyl, ethyl plus terbutyl, and then isopropyl plus terbutyl, right? So all of these different combinations, right? And to be honest with you, I can't remember which is which. But one of these, the dotted line is either the calculated value that he had from quantum chemistry, or the group, what is it? The geometric mean rule value. I don't know which one, right? But in the case here, you can see that in a lot of the cases, the geometric mean rule comes out to be very similar to what he calculates from quantum chemistry. So what is the geometric mean rule that I'm talking about? So if you take the rate constant of species A recombining with species B, that's equal to twice the square root of the rate constant for the recombination of species A with itself times the rate constant of recombination of species B with itself. Okay? So he showed that geometric mean rule works reasonably well for this combination of species. Okay? It's not overly, like there's a big difference here between the green value here and the green value here, right? So they're not overly brilliant, but it's not bad, right? But that work then was built on in a work that was published at the last symposium by Destro et al. And they looked at this combination of species, okay? So I don't know, 2, 4, 6, 8, 10 different reactions, right? And they did the same, something similar to what Stephen did, okay? And what they showed is, look, here's the calculated high pressure limit using quantum chemistry for ethyl plus methyl giving you propane, right? But this is the high pressure limit calculated from the geometric mean rule, okay? And it's in pretty good agreement with what they calculated. They also then can calculate the rate constants as a function of pressure using the geometric mean rule, right? And again, have a look at this paper. It's very interesting, but you can see that it's pretty convincing that it works well. Certainly in the case of ethyl plus methyl giving you propane, right? And then they also showed that, okay, for C1, right, you're at 1 bar, you're at about 30% of the high pressure limit in comparison. Okay, so this is the rate constant at 100 bar, okay, and at 1 bar, it's about a third, okay? The rate constant at 100 bar is about nearly 90% of the high pressure limit, okay? But actually, as you go higher in number of carbons, right, then even regardless of what pressure you're at, you're closer to the high pressure limit, right? So if you have methyl plus C5, right, that at 1 bar, the calculated rate constant is about 90% of the high pressure limit. Okay, that's what's predicted. So this is just then synopsizing it. The geometric mean rule applies not only at the high pressure limit, but also across the entire pressure range explored. And that was shown for the ethyl plus methyl system. For small alkyl radical combinations, the geometric mean rule accurately estimates rate constants with a maximum deviation about 22% in the fall-off region. The geometric mean rule approximation allows for the development of pressure-dependent reaction rate rules for large N-alkyl radical combinations, and it's a useful tool for predicting high-pressure effects that affect the rate at which alkyl radicals recombine. Okay, so it's useful for getting the pressure dependence and so on right for all those molecules. Okay, so that's unimolecular decomposition. H atom abstraction from the fuel occurs by different species. Hydrogen atom, OH radical, HO2 radical, methyl radicals, etc. So the hydrogen atoms can be extracted from primary, secondary, or tertiary carbon sites. Okay, and in alcohols and other oxygenated species from other different sites too, right? So the rate constant depends on the radical species and the type of hydrogen atom being abstracted. The most difficult one to abstract is a primary, then a secondary, and then a tertiary. Okay, and so, okay, and also this initiation reaction, these were actually studied by, again, Ray Walker and his group back in the 90s. And he had an interesting paper published at the Symposium in 1994, where he looked at bimolecular initiation of fuel plus O2. And if you're generating a radical, okay, so in other words, if you're abstracting from an alkane, they recommend a rate constant of 7 times 10 to the 12 on a per H atom, or on a H atom basis, right? Times the exponent of minus delta H of reaction over RT. Okay, so all you need to do to estimate this is say, okay, calculate the delta H of reaction, that's the activation energy, and then whatever number of hydrogen atoms, multiply that by 7 times 10 to the 12, and that's your rate constant for H atom, for that reaction, fuel plus O2, giving you fuel radical plus HO2. All right. But actually then, for allyl radical, you have exactly the same expression, except the frequency factor is different by an order of magnitude. Why is that? The rotors that are in the system. So here, if we have an alkane, we have 2 rotors either side of where we're abstracting. But for an allyl radical, there's only 1 rotor. And actually, when you abstract the hydrogen atom, this rotor here gets tied up and you lose the rotor. And because you lose the rotor, the frequency factor is lower by an order of magnitude. And that's just for allylic hydrogen atom abstraction. Okay? Allylic hydrogen atom abstraction. Because when you abstract it, you lose the rotor that you had before the abstraction. So the frequency factor is an order of magnitude lower. Okay. Now, why am I including these slides? And it's, okay, the main reason I'm including this slide, and it's actually a very nice slide. It was developed by Sung-Ryan Chen. He was working with Scott Goldsborough at Argonne National Laboratory. And what we're looking at here is like we have a fuel, and here's the chemistry related to this fuel, all in blue. And blue, it has its core chemistry as well, right? And then, but we have another fuel molecule. So let's just pretend, for instance, this is N-heptane, right? We have another fuel molecule, this is isooctane. It has exactly the same types of reactions related to it, and we include all the different types, okay? And it will have a different core chemistry, actually, right? I would like to depict it in green here. So the question is, which core chemistry do we use? But that isn't the point of this slide, right? The point of this slide is this, right? The fuels compete with one another for OH, HO2, and CH3O2 radicals at low temperature, right? And so if we have accurate rate constants for abstraction by those radicals, and the absolute rates are correct for both fuels, we should then get an accurate prediction of the effect of blending one fuel with the other, right? Because I found, and we found, typically we found, is that, you know, alkyl radical produced here, it doesn't abstract, or at least these reactions don't show up as being sensitive. So if I have an alkyl radical from isooctane, it's not important to include abstraction from N-heptane, giving you an N-heptyl radical. Those reactions don't show up as being important and don't appear to really occur, right? But what does occur, of course, is abstraction by OH. Now, in the work here that was published in this paper, they do point to the importance of from acetaldehyde plus OH and HO2 and having accurate rate constants for those in blends of ethanol with a primary reference fuel mechanism. Okay, because in that blending, here's the predicted reactivity for pure ethanol. Here's the predicted reactivity for that's E100. What's E0? This is whatever fuel it is. I don't know whether it's a primary reference fuel or it's N-heptane. I'm not sure, right? Maybe N-heptane, right? But you can see that the model is not predicting the reactivity of E30 very well, right? It's a bit better for E10, and E20 is not great either, okay? So the more ethanol that you have in this blend, it's not getting the chemistry right, okay? So the first thing we need to do is to look at the rate constants for abstraction from ethanol by OH, HO2, and CH3O2, and then also in the fuel, if it's N-heptane or whatever it is. But what they found was that didn't help greatly. What really helped was the fact that actually ethanol gave a lot of acetaldehyde, and then having good rate constants or paying attention to the rate constants for acetaldehyde plus OH, HO2, and CH3O2 helped predict the blend. But acetaldehyde is a major intermediate in the oxidation of ethanol. Okay, so that was a particular, I would say, deficiency in the model where probably there wasn't a lot of attention paid to the acetaldehyde chemistry in the model up to that, right? But in general, what I want to highlight and why I have this in red here is that when you have dual fuel or multi-component mixtures, what really matters is competition for those three radicals, right? And if you have good rate constants for those reactions in your mechanism, you should be able to predict the blending effect quite well. Okay. I don't know what. Okay. Okay, so reaction rate rules then make the assignment of reaction rate constants manageable. So here I have a table. This is published in 2006, and it's not just me. This had been done before, but it's taken from the work that we did because it was easy for me to get my hands on it. But other people had done this too prior to this. And what I've done here is just tabulated, right, the rate constant that we use in the mechanism for abstraction by H, OH, CH3, and HO2 on a per H atom basis, okay? So if you have you're abstracting a primary hydrogen atom by H atom, this is the rate constant expression. And you can see then abstraction of a secondary hydrogen atom has a lower activation energy barrier, which makes sense because the secondary CH bond is weaker. And then the tertiary is lower again. And then OH, abstraction by OH, you can see actually the activation energy barriers here are very low. They're almost zero, right? Abstraction by methyl, again, is very much dependent on the bond strength of the CH bond that you're abstracting. And abstraction by HO2 is also very strongly dependent on it. Yeah.
In second case, abstraction by OH radical, secondary is lower than
Negative. No, well, it's not. Okay, and you'll see in a minute. Okay, it's just it's a 3-parameter fit. Remember, A, N, and E, A. So you have curvature and so on, and you'll see it plotted in a second. Okay, but it's not. But it looks like it is, but it's not. Okay, so you were right to ask. Okay, and then you also then can tabulate not just for alkanes, but you can calculate for vinylic, which are these green ones here. So these are they called secondary vinylic and tertiary vinylic, and then you also have allylic. Here, these are secondary, and you can also have tertiary allylic. Okay, hydrogen atoms. Okay, and you can then have rate constants and rate rules for abstraction by them as well. Okay, and tabulate them. Okay. All right. So if we just plot just for a second, and I think this is interesting, right? H atom abstraction from the fuel by the different moieties. So you have H, OH, methyl, HO2, and O atom. And you can see H is very fast, right? OH is fast, and O atom is fast, right? And really, it doesn't look like methyl and HO2. Certainly HO2 doesn't look like it's important. But remember, what is the rate of reaction dependent on? It's the rate constant times the concentration of the species, right? So you have to consider the rate constant, but also the concentration of the species. So at low temperature, do we have much H? Sorry, I didn't accentuate this, but what's important? I should have said this, and now it's good that I meet it now. What's important at low temperature? What's the radical that's most important at low temperature? No, low temperature. It's OH. Why? Because the branching. I should have highlighted this, and I apologize. The branching channel at low temperature gives you a carbonyl hydroperoxide plus OH, and then the carbonyl hydroperoxide decomposes to give you a carbonyl alkoxy radical plus another OH. So at low temperature, the important radical is OH, right? At intermediate temperature, what's the important radical? HO2 and OH, right? And don't forget OH, still important. Why? But what's producing the OH at intermediate temperature is the HO2, okay? So HO2 becomes important, but OH is still the important guy, actually, but HO2 is the radical that produces it, okay? So OH and HO2 are the big ones at low temperature. Then if you go higher in temperature, up at 2000 Kelvin, or we'll say even at 1300 and above, yes, H, OH, and methyl become important. Okay. So OH and H are the most reactive. O radical is also very reactive, but usually it's in small concentration, right? Or O atom. And then HO2 is noticeably less reactive, but leads to H2O2, which then composes into 2 OH radicals. So that's important. So if we then plot OH radicals, we look at the plots of OH radicals, which is what you were saying, right? Here it is actually. Here's primary, here's secondary, and here's tertiary. So actually, secondary is faster than primary, and then tertiary is faster than secondary up to a certain temperature, about 1100 Kelvin, and then it becomes slower than secondary. Okay, just because of the shape and the expression. But this is what was calculated. I actually take the rate constants from Frank Tully. Okay, he did a lot of good work on looking at fuel plus OH. Okay, and then on a per C site basis, so you're taking degeneracy into account. So if you have primary, you have 3 primary hydrogen atoms. If you have secondary, you have 2 secondary hydrogen atoms. And if you have tertiary, you just have 1, typically. Okay? So if you do that degeneracy thing, you can see that tertiary tend to dominate over secondary dominate, then tertiary, and then primary at low temperature. Okay, so the secondary ones are important. Okay, now this is very unusual, right? And it's not normal to do this. But this is a very nice study by Sivaramkrishnan et al. Again, this is a study done by Joe Michael at Argonne National Laboratory back in 2009. And what they did was they looked at, we'd say, propane and N-heptane. And this is for H-atom abstraction by OH radicals. And what they're doing is that they have P1 and P1 dash, and then we have S01, and then we have S11 and S11. And what they're doing is they're distinguishing between S01 and S11 hydrogen atoms, right? So here you're abstracting a hydrogen atom from a carbon which is bonded to a primary carbon and a secondary. So yeah, that's an S01. And here you're abstracting a hydrogen atom from a carbon which is bonded to two other secondary carbons. So that's an S11. Okay? And they're then saying, okay, we have different Ray constants for abstraction of those two different types of H atom, right? Why do they do that? Because they actually, they did do it and they measured different Ray constants, right? And actually, in my mechanisms, we don't do it, right? We just do the simple one where we have primary, secondary, and tertiary. We don't do this level of distinction, okay? But they actually did do it, and you can actually include this level of distinction in your model to make it that much more slightly accurate, okay? Because abstraction by OH is so important, particularly at low and intermediate temperature, low and intermediate temperature chemistry, okay? And then I keep going on about that again, uncertainty in fuel plus HO2 rate. There's less uncertainty than there was, I would say. But here, the solid lines here are Ray constants that we calculated from Karlsruhe in that study that I was talking about earlier. The dashed lines are the Ray constant calculated by Colorado School of Mines. And you can see that the Ray constants calculated by the Colorado School of Mines are always considerably faster than the Ray constants that we calculated, right? What does that do to predictions? Okay, here's an example, right? So here, actually, we've stuck with this Ray constant. We keep this in our model still. We're using this secondary Ray constant in our model, okay? But if you use the Colorado School of Mines Ray constants, it leads to faster predictions. And actually, in this particular comparison, we have a mechanism which predicts better the experimental results because the HO2 Ray constants are faster from the Colorado School of Mines in comparison to the ones from Karlsruhe at Galway, right? Okay. So, but you can see in the temperature range in which these are important, okay? So the temperature range in which that's important is about from 700 up to 1250 Kelvin. Exactly the range that I've been saying that it should be important, okay? You see it there, right? So you use a faster rate, the predicted reactivity is faster. You use a slower rate, the predicted reactivity is slower, right? Okay, so you can use Evans-Polyani type plots. And basically, an Evans-Polyani relationship, I just want to introduce this, is that you can relate the activation energy of reaction to the enthalpy of reaction, okay? And I won't, okay, I can do it here. Okay, so here we have an alkyl radical, and we have an A, N, and EA. but this EA is calculated based on this equation here and the delta H of reaction. Okay, and then this F factor is used. And this slide is courtesy of Peter Alexander Glaude. So you can get ray constants for abstraction estimated based on an Evans-Polyani. I come to maybe I'm not sure whether I will or not. If I won't, I'll come back to it again. Alkyl radical beta scission. So that's, we've now done unimolecular fuel decomposition and H atom abstraction. What about alkyl radical beta scission? And typically, I need to speed up a little bit. Typically what we do is we look at this in the reverse direction, the exothermic direction. It's a radical addition to an olefin, giving the radical. And then we estimate the ray constant in the reverse direction from the thermochemistry. Okay? Why? Because the activation energy for an alkyl radical addition across a double bond in ethylene always has the same activation energy of about 1.2 kilocalories per mole. And then in the exothermic direction. And then in the forward direction, we have to take that plus delta H reaction, and we have the activation energy in the first direction, in the forward direction. But that can be calculated from the thermodynamics of the species when we provide it. All right. Okay. And again, you can, and here's an easier relationship. So again, here now, you can use an Evans-Polyani type correlation for these decomposition. I'm going to show you something different in a minute, but just so you understand the Evans-Polyani relationship. Here, the activation energy for alkyl radical decomposition is equal to 0.6 times the delta H of reaction plus 14.3 kilocalories per mole. Right? This is what's calculated in the study. So again, this is from Pierre Alexander Glaude. Okay, for these radical beta scissions. So if you take these radicals, right, delta H of reaction is this, and then the calculated activation energy are these values here. Okay, and here's just showing you the Evans-Polyani relationship. So you have EA on the y-axis versus delta H of reaction on the x-axis. And you can see for different species, these are the data that were are plotted. So these were actually reactions for which the activation energy was measured. And then you can calculate delta H of reaction. And when you perform this plot, you get this fit line. And this line is equal to 0.6 times the delta H reaction plus 14.3. So that's where that value came from. So I just wanted to see an Evans-Polyani plot. We often do this for ray constants for abstraction by O2, HO2, and so on. That's what we used to do in the olden days to get the ray constants for reaction. Now you do it by quantum chemistry calculation. Okay, but these worked, and they work well, right? And it's good for estimating ray constants. Okay, another way to estimate this is the way that I would do it. Okay, and this is just a nice story and I looked at this maybe 10 years ago. So here we have N-propanol, right? And that can undergo H-atom abstraction at 1, 2, 3, 4 different sites, forming 4 different radicals, right? Okay, so we form those radicals, and here's probably the easiest one to form. Remember I said the CH bond is the weakest. Why? Because of the electron withdrawing oxygen atom bonded to the carbon, weakening the CH bond. And hence, the ray constant for abstraction of this hydrogen atom is going to be the fastest, giving us this radical. Okay, that radical, when it's formed, can undergo beta scission. So it can cleave. So what's beta scission? It's breaking the bond that's beta to the radical site. Okay, so this OH bond is beta to the radical site. So you get this aldehyde plus H. Okay, if we break this H bond beta to the radical site, we get this propanol plus H. And then we can break this CC bond beta to the radical site, and we get vinyl alcohol plus methyl. Okay? So we can get three different product sets from this one radical, right? So the question is then, which one do we get? Or do we assign a third, and say, that's it, lads, off we go, okay? And the answer is no. We have to estimate the rate constant. So what we do, or what I do, is estimate the rate constant in the reverse direction. It's H atom addition to the oxygen atom in this CO bond to give the radical. It's methyl radical addition to this carbon atom to give this radical. It's H atom addition to this carbon atom here to give this radical. Okay? So how do I estimate the rate constant in the reverse direction such that I get the rate constant in the forward direction? Okay. So that's the way I look at it. Okay. Just to introduce it more fully, Craig Tages published a paper in Science in 2005 with others and said enols are common intermediates in hydrocarbon oxidation. And they showed that vinyl alcohol was detected for allene, propyne, and all of this, but also for 1-propanol. So if I just go back for a second, this is vinyl alcohol. So it's detected for 1-propanol. Where is it coming from? Probably this step, right? So they did see it. But actually, vinyl alcohol, or ethanol, was below the detection limit for 2-propanol flames. So just bear that in mind as we go through this. Okay, so as I said, we look at these reactions in the exothermic direction. H atom addition to ethylene, or methyl radical addition to ethylene. Okay, and then we allow the reverse activation energy plus the delta H of reaction to give us the activation energy in the forward direction. And that delta H reaction varies from one reaction to the next. It's not constant. But the reverse activation is. Reverse activation energy is. Okay, so we have these three steps. So what I published this paper in 2006 where we looked at H atom addition to ethylene, H atom addition to propene. If we look at H atom addition to ethylene, terminal H atom addition to ethylene will give you ethyl. Terminal H atom addition to propene will give you isopropyl, and internal H atom addition to propene will give you N-propyl. Sorry, N-propyl, yeah. And then terminal methyl addition to ethylene will give you N-propyl. Terminal ethyl addition to ethylene will give you N-butyl. And internal methyl addition to propene will give you sec-butene, butyl. And internal methyl addition to propene will also give you isobutyl. And then here we have methyl addition to isobutene will give you a neopentane. And what we see here is, if we just look at, don't mind the A and the N, we just look at the activation energy. You see that terminal H atom addition to either ethylene or propene has an activation energy of about 1.2 to 1.4 kilocalories per mole. So let's say 1.3 on average, right? But actually, it doubles to 2.6 if you have H atom addition to the internal carbon atom in propene, right? And then methyl addition, terminal methyl addition to all of these species here has an activation energy of 6.1, but internal H atom addition, well, 6.1 to 6.8. These are actually terminal, I should say. But this is internal addition, and that's, again, higher by about 1.7 kilocalories per mole, right? So it seems like if you have terminal addition, the activation energy is one thing. If you have internal addition, it increases by about between 1.5, 1.7 kilocalories per mole, something like that, right? So, but that isn't the alcohol. So we were, at the time, we were studying alcohols, and I asked John Simi, would he do some quantum chemistry calculations where we could check to see what is the activation energy barrier for these different additions. And what he calculated, he said, okay, H atom addition to ethylene, he calculated using CBS APNO to be level to be 1.3. In the study, I had said 1.45, right? For H atom addition to, apologies, for H atom addition to propene at the terminal end, he calculated 0.81, I said 1.23. Not too bad, right? And then for this species, okay, again, H atom addition to the terminal carbon atom in vinyl alcohol, he calculated to be 0.72, but I didn't do it because it wasn't there. Okay, and then internal H atom addition to the internal carbon atom, he calculated to be 2.34. I said 2.62. But for this radical, when the OH, so for the internal carbon atom addition here, for H atom, he calculated 3.68. And there was nothing to go on. Okay? But his calculations and what I had been calculating were very similar, and certainly gives you some idea of what the activation energy barrier should be. And it means that, okay, if we have in the vinyl alcohol, the OH group is removed from, well, at least one bond removed here, but it does seem to lower the activation energy for addition to the terminal carbon atom. But similarly, here, when you're adding to the carbon which is bonded to the OH, it certainly raises it in that case, okay? And then if you have methyl addition, we say the same thing. His calculations, he calculated 6.4, 6.2, 6.6. So you could say 6.3, 6.4 as an activation energy barrier for terminal addition of a methyl radical across the double bond. I was saying 6.13, very similar, right? And then here he calculated 7.53. I said a little bit higher, and he says higher by 1 kilocalorie per mole. I was about 0.7, right? Within 0.3 of a kilocalorie per mole in the difference, right? So it's still reasonably good. So it's giving some idea. And then for internal addition here, he's calculating 8.91. We had nothing to go on. But this is, again, consistent with the much higher activation energy barrier when you're adding to the carbon which is bonded to the OH for H atom, right? So they're consistent. Okay. So now I want to look at methyl addition to this carbon atom, methyl addition to this carbon atom, the terminal, which is then bonded to the OH. And I'm going to estimate the rate constant of that, right? And so what I do is I say, okay, if I have methyl addition here, I'm going to estimate the rate constant to be the same as for CH2, CH3 in propene, right? So that rate constant was 1.76 times 10 to the 4, 2.48, and 6.13 kilocalories per mole, right? So that's my forward rate constant. The reverse rate constant comes out to be this. Okay, for H atom addition to the oxygen atom here, this was my estimate. I'm not going to go into the details, but it's reasonable. And then here, the H atom addition here was the same as H atom addition to the internal carbon atom in propene, as I had before. And then when I do that, I get, so this is the reverse direction, this is the forward direction rate constant. Okay, so they're color-coded. So the red one is giving the aldehyde, the black one gives the vinyl alcohol plus methyl, and the blue one gives the propene all plus H. Okay. When I plot them, these are the rate constants. And you can see that the vinyl alcohol rate constant is much faster than the others. Okay, so it's not a third at all. It's 90-something% vinyl alcohol plus methyl, right? Okay. Again, this is probably not perfect. there was some ab initio calculations helping us. Now you can do it by quantum chemistry calculations. But I can do this in 5 minutes sitting at my desk, right? It would probably take 5 months or more to do this by quantum chemistry calculations, right? And if you're developing a mechanism with 6,000 reactions, right, you don't want to be running quantum chemistry calculations for those 6,000 reactions. You need a way to calculate a reasonable rate constant quickly, 5 or 10 minutes, not 5 or 6 months, okay? And that's what I'm trying to show you here. But it explains quite readily why vinyl alcohol is produced from 1-propanol, right? And it's very reasonable, right? Now, let me just finish then, right? So it said it was produced, vinyl alcohol wasn't really produced for 2-butanol, or 2-propanol, right? So here's the radical that you might get from 2-propanol, or one of the main radicals. And that can decompose to give propene plus OH, or vinyl alcohol plus methyl, right? And if I do the same sort of analysis, so here we have methyl addition to, where is it? The internal carbon atom here, we get this radical. Or if we have OH addition to the carbon atom, we get it here. But what it's saying here is that actually the fastest rate, certainly up to about 2000 Kelvin, where they become about the same, right? But at lower temperatures where this study would have been performed, propene plus OH is favored over vinyl alcohol plus methyl, right? And it explains then why 2-propanol, you don't see vinyl alcohol, whereas for 1-propanol, you do. Okay. Okay. So for alkyl radical decompositions, typically we look at these in the reverse direction, estimate the rate constant, putting in these rate constants, and then calculate the rate constant in the reverse direction from thermochemistry. Okay. We can do the same with those two. Okay. I think I've hit on this already. The A factors are lower by about a factor of 10 compared to the corresponding alkane when you abstract an allylic hydrogen atom. Okay. Otherwise, the rate constants are the same for alkenes as they are for alkanes. So we treat, in other words, this is a primary hydrogen atom. This is a secondary hydrogen atom. But this is secondary allylic. This is vinylic, secondary and tertiary vinylic. This is secondary allylic, and then that's primary. And we treat those with the same rate rules throughout when we're doing our modeling. Okay? Okay. And I think that's nearly it. I already spoke about this in terms of the difference in reactivities. I spoke about this already. And this is seen here. Listen, I'm already 5 minutes over, and we're over time, and everybody's wrecked. Okay, let's leave it at that, and we'll pick up again tomorrow. Thanks very much.